So the logarithm's treating you well? Yeah? Okay. So we played with logarithms last time, so now we're going to have to use them to solve equations. Okay, so that's section 5.5, exponential and logarithmic equations. So first we'll do exponential, then we'll do logarithmic. But again, I can give you a few equations that you can probably solve without even learning about logarithms and things like that. This is the equation that I've written on a board a few times. What is the x here? 3. And then the bigger question that I also asked you before, is this the only solution? Because every time we're trying to solve equations, we want to find all possible solutions. And we've seen equations that have 2, 3, 5 solutions already. Is this the only solution to this equation? Yeah, I think so too. Why? Can we justify that answer? How do we know that this is the only solution to this equation? Now, the way you answer that question is the function on the left side, the exponential functions, out of all properties that exponential functions have, one of them, as we talked about, this is a one-to-one function, right? You agree with that? And the one-to-one function means it can only reach a certain height exactly once. So it can only equal 8 once. That's what a one-to-one means, right? All the y values are unique. If I graph it, here is 2 to the x, and 8 is somewhere here. So 8 is a horizontal line, so it only has one solution, right? So the reason why this function, this equation has only one solution, the way it's written, is because 2 to the x is a one-to-one function. Only reaches the height of 8 exactly once, right? So we can use this property, the so-called one-to-one property, let's call it that, one-to-one property. If I give you this equation, 3 to the x equals 3 to the power 17, what do you think the solution is? What does x have to equal to? 17. If the bases are the same, the exponents have to be the same as well. So we'll call it the one-to-one property. If a to the power n equals a to the power m, then n equals m. Basically a definition of a one-to-one function, one way or the other. How is that? Does that make sense? So part of the equations that we'll be dealing with is the ones that have the same base. And if they don't have the same base, sometimes you can tweak the numbers ever so slightly so they do have the same base. So we like that scenario. If the bases are the same, then solving equations is going to be less challenging. So I'm going to give you a few examples, and you'll see how much you're going to like that. So 2 to the power negative 2x plus 1 equals 2 to the power 4. Two bases are the same, right? So since bases are the same, I can equate the exponents automatically. So that means in order for me to solve the equation on the left, all I have to do is to solve this little equation. So I'm just setting the exponents equal to each other. Now this equation can have multiple solutions. if when I said the exponents equal to each other, it's not linear, it's quadratic, well, I have two solutions coming out of the quadratic equation, which is okay. All right. But anyway, so this is easy, right? Negative 2x equals 3, x equals negative 3 halves. We're done. Questions? Isn't this lovely? Very straightforward. Another equation, 4 to the power x squared minus x equals 4 to the power 12. So exponents are equal to, I'm sorry, the bases are the same, so therefore exponents have to be the same. I can use this one-to-one property that results in this equation. They're setting exponents equal to each other. Now, that's a quadratic equation. You have 4 ways to solve a quadratic equation. Just pick one and go with it. How would you like to solve this equation? Subtract 12. Try to factor that, right? Can you factor that? Four and 3, what are the signs? Negative 4, positive 3, right? Multiplies to negative 12, adds to negative 1. Set them equal to each other. So x equals 4, x equals negative 3. So we got 2 solutions, but not because of the exponential part, because of the quadratic part of that equation. So that's okay to still have 2 solutions. Okay? Is that okay? All right. Questions on this? Is that good? Okay. How about this one? 4 to the power x equals 32 to the power x plus 1. Different bases, right? So I cannot just set the exponents equal to each other, but there is a way to tweak each base, 4 and 32, so they are the same. Can I find the common base for 4 and 32? Meaning something to a power equals 4, something to a power equals 32, where some things are the same. Which base would I go for? 2, because I can express both 4 and 32 in terms of base 2. 4 is 2 squared, still raised to the power x. 32 is 2 to the power 5, still raised to the power x plus 1. So I'm just rewriting those expressions so they have the same base. And since we just reviewed the rules of exponents, what do I do with the powers when I raise power to a power? So it's 2 to the power 2x equals 2 to the power 5x plus 5 when you multiply that. Right? Now the bases are the same, so we can set the powers equal to each other. So we get 2x equals 5x plus 5, which is a linear equation we can easily solve. Is that okay? So subtract 5x, negative 3x equals 5. So x equals negative 5 thirds. How's that? Bases were different at the beginning, but then we realized that 4 and 32 do have a common base that we can use. In this case, it was 2, so we express both. in terms of base 2, then we use rules of exponents and got ourselves a linear equation. Questions on that? That makes sense? Yeah? Okay. Let's try this. 27 equals 3 to the power 5x times 9 to the power x squared. So not just bases are different, but also have some kind of a product on the right. But again, it would be a lot easier if I can manipulate each number in there, each base, so it all has a similar base, same base. So 27, 3, and 9 can be expressed as powers of what number? 3. So I can use base 3 here. 27 is 3 cubed. The other guy stays the same. And this is 3 squared to the power x squared, right? So again, proceed with the rules of exponents, see whether we can simplify that. So it's 3 cubed equals 3 to the power 5x times 3 to the power 2x squared. So on the right side, I have a product of two expressions with the same base. So what do I do with exponents when I multiply? Add them. So actually, the other side is 3 to the power 2x squared plus 5x. So now we have what we wanted. We have same bases, so we can just set exponents equal to each other. 3 equals 2x squared plus 5x, which is a quadratic equation. I can probably solve that one. I can factor that, I think. We can just guess. Has to be 2x and x. And to get positive 5 and a negative 3, make it minus 1 and then plus 3, so you get 6x minus x, 5x. So factors into that. Or use the quadratic formula. Whatever you solve the quadratic equation, it's up to you. We'll set each factor to 0. So x is 1/2, x is negative 3. So we have two pretty solutions. I don't need to check them because the domain of exponential functions is all real numbers. So whatever we get should work theoretically, unless you made an error. So there's no extraneous solutions here. That's what I'm trying to say. Whatever we get will work. If I take 1/2, plug it all the way back into the original equation, I don't know if I want to, but 1/2 in here, it's 5/2, right? I don't want to, I'm done. Yeah, it works. Yeah, just have to compute. So questions on how we got that one. That one really checked your rules of exponents. You have to really mess with this to get to the pretty state. Questions? Okay. Well, here's an example where the base is what? 3 and 8, and there's nothing I can do to turn 8 into a base 3, right? I mean, if I can, then I'm just solve this equation, because that's what the question is. What 3 to what power equals 8? And so these bases are different, so I cannot use whatever we just did. So in this case, use logarithms. Because we have a wonderful property, the power rule, that allows us to bring the exponent down, right? We have that rule, the third law or whatever. So if a logarithm would magically appear in front of 3 to the x will just fall out. So I just have to decide which log to pick. Since I have to be plugging things in the calculator, I only have two options, either go with the natural log or with the common log. It doesn't matter. If I use the natural log, I'll get something like this. ln of 3 to the x equals ln of 8. So really what I'm doing, I'm taking natural log off both sides. It's a composition situation. By the power rule, x falls out. X times natural log of 3 equals natural log of 8. And this is a linear equation. Because I have a variable times a constant equals another constant. So that's linear. Just divide both sides by ln of 3. So x equals ln of 8 over ln of 3. And this is something I can plug in my calculator, I think, if I can use it. So natural log of 8 divided by natural log of 3. So 1.89-ish. And we're done. Questions on this one? Why did I use natural log? Personal preference. What if I had another personal preference? What would I have used then? Yeah, common log. I probably wouldn't, maybe a personal preference is log base 7. You can use that, but then you're going to be in a whole other world of pain to use change of base formula. Really, all I'm doing, I'm just rederiving a change of base formula. ln of 8 over ln of 3 is log base 3 of 8. That's what it is. So yeah, if I had a different personal preference, I could have used the common log. I could have started with 3 to the x equals 8, and then take log of both sides. Nothing wrong with that. The little x will still fall out. X times log of 3 equals log of 8. Still a linear equation. Divide by log of 3, you get x equals log of 8 over log of 3. If I plug that in a calculator, I should get the same answer. I shouldn't be getting a different answer. So 8 log divided by 3 log. So 1.89. So we still get the same result as expected. So it doesn't matter whether you use natural or log. Personal preferences. I prefer natural log because it's, well, 2 letters instead of 3, just shorter. Okay? Well, natural logs are more natural. That's a different story. So how much sense did that make? So when you have an equation where the bases cannot be manipulated, like before, use logarithms. If you have an equation that has already base e or base 10, then probably use natural log if it already has a base e. Use the common log if it already has a base 10. But if neither one of those appear, then use either natural or common log. Now what I mean by that, let's say you have this equation, e to the power 2x minus 1 equals 7. So I already have base e, so it's wiser to use natural log. You can still use common log, which just be a little messier. With natural log, it will be a little cleaner. And I'll do both, and you'll see what I'm talking about. So if you already have base e, apply natural log to both sides. Because what happens to the left side when you have a natural log of e raised to whatever power? What's going to happen here? Well, whatever the power is, right? Natural log of e just cancel each other because it's a compositional function, it's inverse, and you're left with the exponent, it's 2x minus 1 equals natural log of 7. Linear equation, I can easily solve that. Add 1 to both sides. 2x equals 1 of 7 plus 1. Divide by 2. So whatever that is, that's our solution to this equation. 7 natural log plus 1 equals all of that divided by 2, so 1.47 or so. Is that okay? If for whatever reason you used common log on this equation, that's your just personal preference, no matter what, you just use log base 10, you'll still get the right answer. It'll just be a necessary amount of extra work. So if I do that, so the only thing that happens, don't write this down because you don't want to see that in your notes. The whole exponent just falls down, so it is 2x minus 1 times log of e equals log of 7. Right? Divide both sides by log of e. 2x minus 1 equals log of 7 or log of e, which is the natural log of 7 anyways, change the base formula. And then add 1, and then divide by 2, same way, you get log of 7 over log of e plus 1 over 2. You plug that in your calculator, it'll give you the same answer, but there is a little bit of extra work in there. Where's my calculator? Here it is. So what is this? 7 log. Where's my E button here? That's something wrong. See, I cannot even compute that. It's so awful. That's E. Take the log of that. Put it in the denominator. Times 7. Yeah, that's a little better. Anyways, see what I'm talking about? Extra problems that we don't want to have. Yeah, same answer, but a lot of that. Okay? So, what is the message? Well, if you already have base E, okay? If it's either, then it doesn't matter. But if it already has base E, use natural log. If it already has base 10, use common log. Okay? But if it doesn't have either, then it doesn't matter. So let's say I have this example. 28 to the power x equals 10 to the power negative 3x. Again, I cannot manipulate this basis to be the same, so I'm going to use logs. I already have base 10 at least once, so which log would be easier to use? The common log, because the bases will just cancel. So use the common log here. So we have log of 28 to the power x equals log of 10 to the power negative 3x. So what's happening is the exponent is going to fall out on the left using the power rule. X times log of 28. While on the right, what is the right-hand side going to equal to? Negative 3x, just the exponent. Okay. Well, that's a bad example, but anyways. This is a linear equation. Looks ugly, but it's linear. All the x's are on the same level. There's no powers or anything like that. How do we go about solving this? Okay, so if I do that, so I have x equals negative 3x over log of 28. But I still have, so I'm going to be back where I started. Why would you do such a thing? What if x equals 0? Can you still divide by that then? So in general, it's really in bad taste to divide, and this goes for any equations. Don't divide by things that can potentially equal 0, because you can be potentially dividing by 0. If you're absolutely certain that expression you're dividing by can never equal 0, then go ahead and divide. So things that you can divide both sides of the equation by is this. That can never equal 0. Do you agree with that? It's just something positive plus 1. That's definitely not 0. So it's okay to divide by that. It's not okay to divide by this, because this potentially can equal 0, right? So if you do that, you're going to lose a whole bunch of solutions, potentially. It is okay to divide by something like that, because e to the power x can never equal 0, right? Remember, the range of the exponential function is strictly positive, not 0. It is not okay to divide by something like that, because this can equal 0. Natural log of x equals 0 means x equals what? What is the solution to this equation? 1, right? Log of 1 always equals 0. So this is okay, this is not okay, this is okay, this is not okay to divide by. So when you're dividing by x, x can be 0. Actually, it is a solution to that equation. Because look, if I divide both sides by x, where's my equation? I already wrote a whole bunch of stuff all over it. See what happens. If I divide both sides by x, I'll get log of 28 equals negative 3, right? That's, no solutions, because log of 28 definitely not negative 3, right? But look back at the original equation. If I let x equal 0, if I plug 0 for x, I'll get 0 equals 0. So hey, that works. So what you just did, you divided both sides by 0, and your equation just broke down. So the message here, do not divide by things that have variables, because you're potentially dividing by 0. Are you with me on that? All right. Well, let's go back to our original equation. How can we solve that? I mean, we can, now I told you what the solution is, but what would be the proper way of getting the answer? Let me give you this equation to solve. How about just 28, well, okay, 2x. I meant 28, 2 came out. Can you solve that equation? How would you go about solving that equation? Add 3x. You want to group your variables on one side. What are you going to do with this? What is that going to give you? How do you know that? That's true, but besides that, uh, come, what? How did you get 5? And what two numbers were you adding? 2 and 3, and 2 plus 3 equals 5 by properties of addition. I'm not arguing with that. There is a reason to this line of questioning, and we'll see in a minute. But you focus on just 2 and 3, and you realize the x is just not going anywhere. So that's how you combine like terms. X stayed, and you added the coefficients. 2 plus 3 equals 5. How do you proceed? Divide by 5. X equals 0. Again, that's why dividing by 0 was a bad idea there, because x is in fact 0. Okay. Let me take that back, because that's not the solution to the equation that we did originally. But anyways, so let's mimic those steps. Let's take the same steps we used on a simple equation with this guy. So what do we do first? Add 3x. So 0, what's going to happen with all of that? So what is log 28x plus 3x? Can you write it in a more condensed version? Can you do the same properties of addition you applied on a simple equation when you went 2 plus 3 equals 5 over here? Well, the answer is no, because it's not going to be something nice and pretty, but you understand what you're thinking about, and I hope that's the thought that was running through your head. How do you add log of 28 and 3? That's what you were thinking, right? You were not worrying about the x. You realize you just have to add the coefficients. So that's just going to be whatever log of 28 plus 3 is times x. That's, you're just kind of factoring the x out. Just like over there, you did 2 plus 3 equals 5. Well, here you have log of 28 plus 3 is log of 28 plus 3, but it is a constant times x equals 0, so to solve, it's 0 divided by log of 28 plus 3 still gives you 0. But that's the idea. When you cannot group them, you kind of factoring the x out. You realize you're combining like terms, so you're just adding the coefficients, so just keep them as a single unit. Because there's nothing you can do with log of 28 plus 3. You can plug it in a calculator, but no. So that's that. Was that good? Good. Well, let's try another messy one. (14 to the power negative 2x plus 1 equals 10 to the power x minus 1. How should I start? Common log, because again, I see base 10, so I'm going to use common log. It'll just make things a lot quicker. So we'll take log of both sides of this equation. So using the power rule on the left side, the exponent falls out. Negative 2x plus 1 times log of 14 equals, what's going to happen on the right? Yeah, so they just cancel, x minus 1. All right. That's a linear equation. All x's to the power 1, they're all kind of nicely on the same level. How do we solve that? So get everything to the left. Okay. Well, before we do that, just to make sure we're on the same page, let's say I don't have log of 14, I just have 14. Just forget about log for now. Let's solve this equation. How would you solve that equation? What would you do first? Distribute 14. You would open up the parentheses, because that's the linear equation. The way we solve linear equation, we group the variables on one side and we move the constants on the other side. So yeah, distribute 14, so whatever, negative 28x plus 14 equals x minus 1, right? Yeah. What are you going to do now? Just on the simple equation. Add 1. Still subtract x? No. No. Add 28x. So you get 15 equals 29x. So you want to have x's on one side, constants on the other side, right? What? Right? Yeah, okay. And then you just divide, so x is 15 over 29. So again, we're going to do the same thing with this logarithmic equation. Well, not logarithmic equation. It's still linear equation. We just have a weird coefficient. But first, we will open up the parentheses. So you'll get negative 2 log of 14x plus log of 14 equals x minus 1, right? Then I want to group all the constants on the one side, all the variables on the other side. And for some reason, we were adding 1 there, so let's add 1 here and add 2 log of 14 times x on both sides. So what appears is that we have log of 14 plus 1 equals x plus 2. Well, let me write it like this. 2 maybe x log of 14, just for no particular reason. I just don't want that x to feel like it's inside the log. Kind of what we were doing. So, well, remember from the previous example, there's no way I can add this coefficient. The coefficient here is 1, and the coefficient there, it's 2 log of 14. The only way I can get x in just one spot is by factoring. So really what I have now is 1 plus 2 log of 14 times x. This is how you combine like terms. You just add coefficients. This is how we went from x plus 28x is 29x. You just went 1 plus 28. So we're doing the same thing here. We're just adding the coefficients. So then the x would be just dividing both sides by the coefficient. So it's log of 14 plus 1 over 1 plus 2 log of 14. Right? I can plug it in a calculator at this point. It looks kind of messy and ugly, but I can kind of do that, right? 14 log plus 1 equals that. And then divided by, I'm probably going to use parentheses here, 1 plus log of 14 times 2. So 0.65. You should be totally checking my work on your calculators, just to make sure you're okay plugging that stuff in, because it's not easy thing to plug in your calculator. But on your fancy graphing calculators, you can just type it in as it appears. Just make sure you put parentheses around the numerator and the denominator, otherwise the calculator will not give you the right answer. On a graphing calculator, you really want to go like that. got that? So 0.65-ish. Questions on this one? Things getting a little weird, but again, just same steps as you would do when solving a regular linear equation. Just remember here it's hard to combine like terms, so just keep them like that. 1 plus log of 14 is 1 plus log of 14. Plug the answer in the very end, otherwise you're going to lose a lot of points, a lot of decimals in the rounding error. All right, let's try this one. E to the negative, well, for some reason I have c. E to the negative c plus 1 equals 5 to the power 2c. How should I do that one? Take the natural log, because we already have base e. So take the natural log of both sides. The left-hand side explodes into negative c plus 1, while the right-hand side, 2c falls down, 2c times ln of 5. Right? So linear equation, group the variables on one side. So add c to both sides. So it's 1 equals 2c ln of 5 plus c. Right? So again, c appears in two places. In order to combine like terms, I'm going to have to factor the c out. 2 natural logs of 5 plus 1 times c. So this is the coefficient in front of c. So then, to solve for c equals 1 over 2 ln of 5 plus 1. So whatever that is, that's our answer. I can plug that in the calculator. So 5 natural log times 2 plus 1, whatever that is, take the reciprocal, so 0.24-ish. Depending how many decimals you ask to round, 0.237. On the tests, I don't care. I know my math lab will get all picky about that. So pay attention to, the fine print. They'll tell you how many decimals they want. So this is why it's wise to only use a calculator in the very end. This way you get all the decimals correctly, and then, Are we good? Okay. Let's try this example. You'll try this on your own, because I've done enough. Three to the power x minus 1 equals 4 to the power 2x plus 3. You cannot turn 3 into 4 or 4 into 3 or find a common base. So you have to start taking logs of both sides. Since there is no e, there is no 10, doesn't matter. So use your personal preference, whether you want to do natural log or the common log. And I can even give you the answer. I think I have the answer. Nah, I don't have the answer. No, I do have the answer. Answer looks like, oh, it's a cute answer. Almost appears to be negative pi-ish. So what is your personal preference as far as the log goes? What? Natural? I like that. Oh, it's okay. Either way, natural is natural. So do either log of your preference. So what that does, it brings these exponents down. So this gives me x minus 1 times ln of 3 equals 2x plus 3 times ln of 4, right? Which is a linear equation. So just like with any linear equation, you would proceed with opening up the parentheses. So we'll distribute ln of 3 and we'll distribute ln of 4 to get x times ln of 3 minus ln of 3 equals 2x times ln of 4 plus 3 times ln of 4, right? So then, just like with the linear equation, we would group all the constants on one side, all the variables on the other side. So ln of 3 is a constant added to both sides of this equation. 2x ln of 4 is a variable, so move it to the other side. So that gives you x ln of 3 minus 2x ln of 4 equals 3 ln of 4 plus ln of 3. Is that okay? Still a linear equation, an ugly one, but a linear. So again, how do we combine like terms? We have x and x, so we can factor that out. Leaves us with ln of 3 minus 2 ln of 4 equals 3 ln of 4 plus ln of 3. Right? And finally divide. If you properly plug this into your calculator, you should get negative 3.14 or so. How many of you got to this point, but then when tried to plug in, didn't get the right answer? Or you didn't get to that point? Well, you do need a 2. But let me show you how horrible it is to plug it in a calculator given a normal calculator. On the graphic one, you just have to put a lot of parentheses everywhere. But here I have to do what? Natural log of 4 times 3. So that's that. Plus natural log of 3. So that's that. That's my numerator. And then I have to divide it by, and I'm going to probably have to put it in a parentheses, open parenthesis, ln of 3 minus 2 times ln of 4, close parenthesis. Yeah, so negative 3.14. Okay. But there is a way to kind of make that calculator portion go a lot quicker. Because look, these are all natural logs, meaning they all have the same basis. So we have certain properties that allow us to condense natural logs into one. What can I do with the constant in front of the log? What is that rule that allows us to manipulate the constants and exponents? I can take this 3 in front of the natural log and toss it back as an exponent. Can I do that? And I can do the same thing with that little 2. So if I do that, I actually have natural log of 4 cubed plus natural log of 3 over natural log of 3 minus natural log of 4 squared, right? And what is 4 cubed? 64, right? 64 plus ln of 3 over ln of 3 minus ln of 16. Is that okay how I got this part? I'll have addition. The sum of logs become a log of a product. It's the same thing as natural log of 64 times 3. Do you agree with that? That's your power rule. By the quotient rule, the denominator is ln of 3/16. The difference of logs becomes log of a quotient. So all I have is natural log 3 times 64 is 196 over natural log of 3/16. Right? If I plug that in a calculator, 196 natural log divided by 3/16. Okay, I have to be more careful. Let me do 3/16 first. Take the natural log, put it in the denominator, times 196 log down. What? Gave me the wrong answer. It's not 196. What is it? 192. Okay. Thank you. What? Well, thank you. Let's try it again. Otherwise, my whole little theory was falling apart. That's my denominator. Flip it times 192 natural log. Yeah, that's a lot better. So I don't know which one is easier. Plug everything in or do little manipulations and then have a smaller one. But then, of course, you have to multiply 64 by 3. And I'm not sure how I got 196. It's just silly. All right. But either way, we'll get you the right answer. Let's do a fun one. So I have e to the x, and then I have e to the negative x, and then I just have a random constant on the end. So we haven't done anything like that yet. We have a sum or difference of exponentials and a constant on the other end. And then e to the negative x is throwing me off. What does it really mean, e to the negative x? What is the meaning of negative exponents? So good that we reviewed rules of exponents at the beginning of the class. 1 over e, right? So really, this is same as e to the x minus 6 over e to the x equals 1. Right? That's really what this equation is saying. So in addition of being an exponential equation, it is also a rational equation, has denominators with variables in it. So you were taught one thing. If you have denominators, what would be the wise thing to do about those denominators? Which is, in this case, e to the x. What do you want to do with that? So LCD is e to the x. The wisest thing that you can do, multiply both sides by e to the x. You want to multiply both sides of the equation by the least common denominator to get rid of all denominators, right? So this is what we did a few times already when we dealt with rational equations, when we dealt with linear equations that had fractions. Multiply both sides by the LCD. So what happens, this is e to the x times e to the x, which is what? E to the x, but the whole thing is squared, right? Like that. So really it is same as e to the 2x. Now this just cancels, minus 6 equals e to the x. Right? So if I move everything to one side, what does this look like? What? It is a quadratic, right? You have e to the x, and then you have e to the x squared. So it does follow the quadratic pattern. A square, not square, then a constant. So this is the equation of quadratic type. So pay attention to this one. So this is the quadratic type. And the way we do those by substitution. Let u equal e to the x. So then when you substitute for every e to the x you put u, you'll get u squared minus u minus 6 equals 0. So we'll just focus on solving for u first. And then we'll resubstitute, as we did in chapter 2. I don't remember when we did quadratics. This one is factorable, right? Set each factor to 0, u minus 3 equals 0, u plus 2 equals 0, u equals 3, u equals negative 2. Right? I still have to solve for x, so I'm going to substitute back to get e to the x equals 3 or e to the x equals negative 2, and then I'll solve each little one. For x, I mean, this one is just x equals natural log of 3. Right? How about that one? So equation e to the x equals 3 gave us a solution x equals ln of 3. How about equation e to the x equals negative 2? And what is the natural log of negative 2? This is you can compute in your head. This natural log of negative 2 you can compute in your head. Yeah, no solution. Natural log is only defined on the positive numbers, or the range of e to the x is strictly positive. E to the x can never equal negative 2, so this one has no solutions. So even if you go all the way down to natural log of negative 2, that one is undefined. If I take my calculator and I go negative 2, take natural log of that, it gets upset. Right? Okay, good. So yeah, the equations of quadratic type, we're going to have fun with that. Just appeared out of nowhere, but the logic was the same. Oh, we notice we have a denominator. If you have a denominator, kill that denominator. Oh, it looks like a quadratic all of a sudden. Solve that. Yeah. Good stuff? What? This is fun. This is only half of section 5.5. These are your exponential equations. We also got to talk about logarithmic equations. The first type of a logarithmic equation that we'll talk about is something like log base a of x equals b. So you have a logarithm of one log on one side and a constant on the other side. And the way we're going to solve this, we're just going to rewrite in the exponential form, meaning x equals a raised to the power b. So if we rewrite our logarithmic equation into exponential form, we'll be able to solve it. And it'll get rid of all the logarithm part of it. So rewrite in exponential form. So for example, log base 5 of 8 minus 7x equals 3. So just rewrite this in exponential form. The inside of the log, 8 minus 7x, equals the base 5 raised to the power 3. And all of a sudden, that's a linear equation. Right? Remember, this is the base, and this is the power. So whatever you solve here, 8 minus 7x equals 125, looks like. Subtract 8. Negative 7x equals 117. So x equals negative 117 over 7. we kind of do have to check our answers to logarithmic equations, because logarithmic equations do have domain restrictions. Logarithms have domain restrictions. Log is only defined on a positive real number. So you have to make sure whatever the answer you get does not turn the insides of the log into something negative. But if I take a negative 117 times negative 7, it's going to give me something positive, so we're good. Just kind of, that's the check. Make sure the insides of every log in your equation remain positive. Not even 0. You cannot have 0 inside the log. That's also undefined. So strictly positive. Here's another one. 3 natural logs of 3x plus 1 equals 5. So again, I want to make it look like the equation before, just the logarithm equals a number. So first step would be to isolate the log. So subtract 1. 3 natural logs of 3x equals 4. Divide by 3. Natural log of 3x equals 4/3. So now it is in that log equals a constant form. So what is the base? E. So then is the insides equals e to the power 4/3. Right? Base raised to the power equals the inside. So x is e to the 4/3 over 3. Whatever that is numerically, we can plug it in just to make sure. Oops, wrong button. So 4/3 raise e to the power over 3. So there it is. And it is in the domain of our log. How was that? Was that pleasant? Not too bad. So you have to be good at rewriting your logarithmic forms into exponential forms. Now let me give you this equation. See whether we can reason our way to the proper answer. Log base on whatever 8 of x plus 1 plus log base 8 of x equals 2. So we just talked about how I can solve equations that have one log on one side and a constant on the other side. Well, this one has 2 logs on one side separated by a plus and a constant on the other side. So the only question is, can I turn the 2 logs into 1 log? Because if there was a way to turn the left-hand side into just a single log, I'm back to what I just did. So if I have a sum of logs, it becomes what? Yeah, what? Somebody say divide? No one said divide. What should I do? Multiply. So it's a log base 8 of x times x plus 1 equals 2. So using the product rule, the sum of logs became a log of a product. Now it's a single log. I can solve that equation. Again, it's the insides equals base to the power. Right? So it is x squared plus x minus 64 equals 0. Quadratic equation. I can solve any quadratic equation. I don't think I can factor that one. So we'll just use the quadratic formula. X equals -1 plus or minus the square root b squared, which is 1, minus 4ac. C is negative, so minus becomes a plus. 4 times 64, 256. And again, I lost my confidence in multiplying 240 plus 16. I think that's close enough, right? So that is -1 plus or minus the square root of 257 over 2, right? Now, when I have -1 minus square root of 257, so it's a pretty negative number, right? And by pretty, I mean nicely negative. It's not a pretty, but what is it? 257, it's around 15-ish, 16-ish. 16-ish, it's actually really close to 16. Regardless, if I go back to my original equation, it's a negative number, and I have log base 8 of x. Log base 8 of x will not take negative numbers. -1 is the extraneous solution. With a plus, it will work. It'll maintain, it will stay in the domain of those functions. So really the only solution here is -1 plus the square root of 257 over 2, whatever that is. Does that make sense why I didn't take the minus? Not just because it's negative. Sometimes you get negative answers that work, positive that don't work. You just have to make sure it stays in the domain of your original expression. And the reason why I took the positive one, I didn't really check, but and as long as it's in a domain, it will work. Unless you made other errors. You cannot have an extraneous solution that's in the domain. Unlike with the square root ones, you can have an extraneous solution that is in the domain. Is that okay? So we have two logs. We had two logs, and we turn them into one. If I do the same exact problem, log base 8 of x plus 1 only minus log base 8 of x equals 2. Then again, I can convert a difference of two logs into a single log by doing the division. So this is log base 8 of x plus 1 over x equals 2, right? Using the quotient rule. So again, I have log on one side and a constant on the other side. So I can really easily rewrite this in the exponential form. Whatever's inside equals the base to the power. So it's x plus 1 over x equals 64. How do we solve that? Anyone? It's a rational equation, has a denominator. Multiply both sides by x, so times x, that's a times. So you just get x plus 1 equals 64x, so 1 equals 63x, x equals 1 over 63. All right? So that's what happens when you have a log on one side and a constant on the other side. So that's that one type of equations. The other type of equations when you have log equals a log. So it's the same as with exponentials, the one-to-one property. If the bases are the same, the insides have to be the same because logarithms are also one-to-one. So the second type of logs, if you have log base a of n equals log base a of m, this implies that n equals m, just like with the exponential equations, logarithmic one-to-one property. So if I have something like, for example, log base doesn't even matter, base 11 of 3x minus 1 equals log base 11 of 2x. log equals log, bases are the same. That's the only time where base is in the play. You're just checking 11, 11, good. So right away 3x minus 1 equals 2x. Okay? So you're just setting the insides equal to each other. I can easily solve this. Add 1, subtract 2x, you get x equals 1. Right? Questions on that? If I change this just a little bit, log base 11 of 3x plus 1 equals log base 11 of 2x. Same situation. You have logs of the same base on both sides of the equation, so you can let the insides equal automatically. 3x plus 1 equals 2x. Right? Try to solve that. Subtract 2x from both sides, subtract 1. You'll get what? X equals negative 1. Right? Can negative 1 work in this equation? No. Negative 1 is not in the domain. If I take negative 1 back into the original equation, I'll get logs of negative numbers, so that doesn't work, so no solutions here. The only possible answer that we found does not work, so no solutions. Is that okay? If you have an equation that has multiple logarithms, log base 8 of x plus log base 8 of x plus 4 equals log base 8 of 12. It's not log equals log. It's not log equals a number, but I can make it into log equals log, right? I can do certain transformations so both sides of the equation contain exactly one logarithm. I can move these two into the same log. So it's log base 8 of x times x plus 4 equals log base 8 of 12 using the product rule. Are you with me on that? Bases are the same. That's the only time the bases actually matter in these types of equations. Just making sure they're the same. So then by that one-to-one property, x times x plus 4 equals 12. I can certainly solve that. That's a quadratic equation. X squared plus 4x minus 12 equals 0. I can factor that, right? X plus 6, x minus 2 equals 0. X equals negative 6, x equals 2. Am I done? Right. So it looks like negative 6 is extraneous, but 2 works. So that's the extraneous. This is the only solution. So again, those properties come into play. Sometimes you have to turn 2 logs into 1. So if you have a sum or a difference, we can certainly do that. And again, the bases, the only time the bases come into play in this types of problems is just make sure they're the same. If the bases were different, we won't be able to do any of them. Actually, we'll probably be done. We can probably only solve it by graphing. Graph everything and then see where the things intersect. Something like that. Now let's try this fun one. 2 times log base pi of 50. And the reason for pi is just, again, doesn't matter in this case. 50 equals 3 log base pi of 25 plus log base 5 of x minus 2. base pi, that's exactly right. Just making sure you're paying attention. Yes, so yes, I do want those bases to be the same. So probably I'm going to go for the case where it's log equals a log. But there are two things that prevent from that. First of all, the right side is the sum, and also this coefficients in front of logs kind of blocking me from doing anything. But is there anything that can be done? Yeah, I can always toss the coefficients back on top. So do that first. So it is log base pi of 50 squared, whatever that is, equals log base pi of 25 cubed plus log base pi of x minus 2, right? So first get rid of the coefficients by throwing them back as exponents. Then I can combine the right-hand side into log base pi of 25 cubed times x minus 2. So the sum became product. Right? So bases are the same. I can just automatically equate the insides. And that's a linear equation. I can divide both sides by 25 cubed. So it's 50 squared over 25 cubed equals x minus 2. So just add 2 to whatever that thing is. Right? I should reduce that fraction. That's definitely something that we can reduce. The way I would reduce that, I would actually split 50 squared into 25 squared times 2 squared. That's 50 squared over 25 cubed. So I can cancel that and that. So that is 4 25th plus 2. So x is 2 and 4 25th. And that looks like it's in the domain, right? That minus 2 is still positive, so we're good. Questions on this? If you have, so really two cases. Log equals a number, and log equals a log. So just make sure if you have more than one log, you combine them using either the product rule or the quotient. All right, well, that's good. That's our